Gaurav, are we ready? All right. Okay.
Yes, sir, start.
Welcome to this lecture today. Today we are very fortunate to have Professor Balasubramaniam, a renowned mathematician amongst us, to talk about Ramanujam and the relevance of Ramanujam today as part of our Ramanujam Yatra. I'm sure you have joined us through Vigyan Prasar Facebook and Vigyan Prasar YouTube channel, as well as indiascience.in, our internet television. Thank you for being with us. In this program, we'll continue with uh, a presentation by our director, Dr. Nakul Parasar, a brief introduction of what is Ramanujam Yatra, why we are doing it now, what is its relevance, and then we will have Dr. Ramanujam introducing our speaker, and the speaker will make presentation, and in the end, we can take up your question and answer. You can post your question and answer in the Facebook and YouTube. We would be able to access those questions or your comments. So we welcome all the participants to interact through our Facebook and YouTube. Now I would invite our director, Dr. Nakul Parasar, director of Vigyan Prasar, to give an introduction about Ramanujam Yatra. Over to Dr. Nakul Parasar, sir.
A very warm evening, a very warm welcome to all of you. It's indeed my privilege to welcome Dr. Balasubramanian for this lecture series, which has been so far that we have covered the yatra that we have traveled so far has seen people like uh, Professor Ken Ono, Professor Sujata Ramdurai, Dr. Bruce Brent, and now we have very eminent and our own Dr. Balasubramanian. Ramanujan Yatra, as the name suggests, is to commemorate the 100th death anniversary of the great mathematics legend. Ramanujan left all of us in the year 1920, exactly 100 years ago. And on 26th of April, that was the date. And this year, because of the pandemic, a program that we had already planned earlier, that we would all join, be there in Kumbakonam to commemorate, kickstart this program, unfortunately couldn't happen
I'll join in a minute.
because of the pandemic. However, we did a small symbolic program in Kumbakonam with a handful of people where we did some rituals. We've had some small discussions. But then thereafter, we decided and took the advantage of these webinars and these lectures through online media. We also, besides these eminent lectures by people of eminence, where we have Dr. Balasubramaniam today, we've had a parallel session of lectures in Indian languages. We indeed honored, indebted, and highly thankful to Professor Ramanujam of the Indian Institute of Mathematical Sciences to have helped us, to have assisted us, and also had shouldered the responsibility to, not only deliver the first lecture in Indian languages, that was in Tamil, followed by Telugu, Malayalam, Kannada, Gujarati, Marathi, and Bengali. The journey continues, and we'll have many more languages that we shall be bringing to you in Indian languages. December 22nd, which we all know, is the birthday of the great mathematics legend Ramanujan, is celebrated as the National Mathematics Day. This is when we plan to culminate this yatra. So from his death anniversary to his birth anniversary is what this Ramanujam Yatra is all about. And we have all been blessed by various scholars of eminence who've spoken not only in English but also in other Indian languages that I spoke of a while ago. We shall now look into other remaining Indian languages in the times to come. This is indeed a program that was conceived, and this is how we all brought people together under the guidance and leadership of my colleague and dear friend, Dr. T.V. Venkateswaran. So, on behalf of Vigyan Prasar and our movement in Tamil, which is called Arivial Palagai, I once again welcome all of you to this lecture today, and I'm sure you would all benefit from after hearing Dr. Bala Subramanian. And as normally we do in every lecture, we have a question and answer session. So please don't hesitate to ask your questions. Please post them on the chat box that is there in your YouTube, Facebook channels where this is being live broadcasted. So without taking much of your time, I once again thank Professor Bala Subramaniam and also Dr. Ramanujan to have brought the best of the minds in the domain for the benefit of our viewers, or the benefit of our listeners and our audience here. Thank you so much, sirs. We truly appreciate your support and look forward to a very interesting and a very engrossing lecture today. Over to Dr. Venkateswaran.
Thank you, sir. Today we have a very eminent speaker amongst us, Professor R. Balasubramaniam, who is famed for many things. One thing that sticks out is his solution to a problem which was there for about 400 years, in which people like eminent mathematicians like S.S. Pillai had worked. I would request Dr. R. Ramanujan to introduce the speaker before we start the lecture. Over to Dr. Ramanujan.
Thanks, Venkateswaran. It's my pleasure to introduce my dear friend and colleague, Balu Subramanian. Balu is one of the eminent number theorists in India, very well known for his work in analytical number theory and on moments of Riemann zeta functions. He, as Venkateswaran mentioned, he's particularly famous for the theorem G4 equals 19, where he and his co-authors, De Jouvier and others, they solved the Waring's problem in 1986. And Balu is a recipient of many awards, the Shantiswarup Bhatnagar Prize, the highest civilian honor of India, that is the Padma Shri, and the French government's Ordre National de Mérite. And of course, is a fellow of many societies. He was a plenary speaker of the International Congress of Mathematicians, great acknowledgement, recognition by the mathematical community. Well, I should also record with pleasure that he was the director of our Institute of Mathematical Sciences for 10 years and built up the institute in a substantial fashion. So it's a great pleasure to have Professor Balasubramanian here to talk on the impact that Ramanujan had on number theory in India. We have heard about Ramanujan's life a lot, about his mathematics as well. And it's true that he continues to be a tremendous inspiration, and his mathematics has had unforeseen applications of all kinds. We have even talked about black holes and so on, Ramanujan's mathematics. But on number theory itself, I think Ramanujan made a huge impression, and you can't have someone other than a number theorist like Balu talking about it. It's wonderful to have Balu speaking on it. Thank you.
Thank you, Dr. Ramanujam, and he has been one of the pillar in organizing these programs. He has been supporting Vigyan Prasar in catalyzing this whole activity. Thank you for this support. Now I would request our speaker, eminent speaker, Professor Balasubramaniam. Sir, over to you, sir. We are eagerly awaiting your lecture. Thank you.
Thank you. Thank you very much. And I think initially I gave the title something like an impact of Ramanujan on Indian mathematics. And then once you decide to prepare the lecture, you find that the impact is not something which could be covered within an hour. And therefore, I changed it to impact of one idea. One single idea is what I plan to talk about. And this single idea is one of the very important ideas, and you might have probably heard some lectures either from me or Ramana on this topic, and therefore some of them might be probably familiar to you from the earlier when we talked about it. But I think there are more new undergraduate students, and therefore I would be more or less directing my talk towards them. And then about the variance problem, some comments are made, and I plan to talk about the variance problem also. Okay, therefore the one idea which we are now going to talk about is from a paper from Hardy and Ramanujan, and that is this paper, asymptotic formula in combinatorial
Balu,
analysis.
your screen has to be shared. We don't see your screen right now.
Oh God, 1 minute, just a minute.
You should have left the screen on.
Yeah. Okay, just give me 1 minute. We will share the screen.
Hello.
Ah.
Sir, நாங்க ஆல்ரெடி ஷேர் பண்ணி தான் இருக்கோம். ஓகே.
Okay.
நம்ம பண்ணிருக்கோம், பட் அவங்க வந்து
Is it okay?
Yeah, we can see it now. Very good.
Okay, thanks. Yeah, this is this paper, asymptotic formula and combinatorial analysis. And the impact of this paper is what I plan to talk about mainly. And what is the problem concerned in this paper? It's not a difficult problem, somewhat a problem which even high school students can understand. The question is, in how many ways given positive integer be expressed as sum of positive integers? This number is what is called a partition function. And let's start with a specific example of 4. Therefore, given an integer, determine the sequences of integers satisfying the equation x1 plus 2x2 plus 3x3 plus etc. equal to n. By this, I assume that when I write n, then the number 1 comes x1 times, the number 2 comes x2 times, the number 3 comes x3 times, and so on and so forth. And in that case, of course, this n would be equal to x1 plus 2x2 plus 3x3, etc. Because x1 is x1 number of times 1 comes and x2 number of times 2 comes, and so on. And this number is what is called a partition function. For example, if I take 4, then the 4 can be written as 1 plus 1 plus 1 plus 1, which means 1 comes 4 times and every other number comes 0 times. The 4 also can be written as 1 plus 1 plus 2. 1 comes 2 times and 2 comes once. 4 can be written as 1 plus 3. Therefore, 1 comes once and 3 comes once and others is 0, and so on and so forth. And therefore, it is easy for you to check that there are exactly 5 ways when the 4 can be written as sum of the integers. And the question is there a formula which you can write? A formula for which Pn, and even if there is no formula, then whether you can write an approximation. And what they did is that this approximation, they write, let SNM be defined by 1 over pi times square root of 8 into summation over c power half, AC of n, d by dn of e power pi by c square root of t by 3 lambda n by lambda n. And all these things I would explain in a minute. And then they prove that this Pn can be approximated by SNM very well, particularly when m is close to square root of n or even constant times square root of n. And this approximation is so close that the difference is at most k divided by n power 1/4. In particular, if n becomes sufficiently large so that this n power 1/4 will dominate the k, then the difference is at most 1, which would mean that the Pn is close to SNM And in fact, if you compute SNM and take the integer which is nearest to Pn, and that will be the integer. That will be the value of Pn. And here the lambda n stands for square root of n minus 1 over 24. This minus 1 over 24 is something which is a little interesting, and I don't know whether I have time to talk about that. And then this dy dn is something which would be confusing to you, because n is a natural number, and what is this dy dn? But there was a classical notation by Ramanujan, which simply means that you take d over dx, replace n by x, and you have a d over dx, and then do the derivation. After doing the derivation, you put x equal to n. That is what it will be, dy dn. And therefore, with this formula, they were able to prove that you can actually get the value of Pn very close. This SNM is something is going to be easily computed because it has only a sum of square root of n terms, and you take this sum of the square root of n terms and compute that, and that gives you the value of Pn. And that is not, I mean, you can't expect something which is simpler than this, etc., for the simple reason that the Pn actually grows very fast. In fact, P of 200 is essentially a 7-digit number, and therefore you would expect that somehow a complicated formula like that. And now what is this ACN? ACN is a sum of roots of unity. More precisely, ACN is equal to summation epsilon AC e power minus 2 pi I NA by C. And note that e power minus 2 pi I NA by C is a cth root of unity. And this epsilon AC, which I have not defined, is a 24 times C root of unity. And therefore, both epsilon AC is a root of unity, e power minus 2 pi I NA by C is also a root of unity. Totally what you have is a root of unity, and any root of unity has an absolute value 1, and therefore you are actually summing up something of absolute value 1 between 0 and C. And that something was absolutely 1, there is possibility that there is a cancellation. Even if there is no cancellation, then the ACN can be at most C. And that is something we will be needing a little later. Therefore, for large n, the integer Pn is the integer which is closest to SNM, where m is square root of n. Now, therefore, now let's put Pn equal to SNM plus Rnm. I am not going to choose my m to be close to square root of n. I take a general m. I take a general m and then write an SNM. And then I would like to know whether this SNM converges and whether it converges to P of n and how close the convergence is, and so on and so forth. I mean, what is sanctity? It essentially restricting the summation only up to m. Therefore, the m around the square root of n, of course, you have this formula, which is Rnm is very small. It is k times n by k divided by n power 1/4. But for a general m, is it possible to give an explicit bound? And also, is it true that the SNM converges to Pn as m goes to infinity? If it is not possible, then is there some modification which you can do, some standard functions, and then try to see whether that converges to Pn? And it so happens that this SNM does not converge. But then if you do a slight modification, it converges. And therefore, let me go back to this. In the SNM, you have something like an e power pi over c within the derivation, dy dn of e power pi over c. And what Rademacher did was that e power pi over c, he replaced by sine hyperbolic pi over c. And now the sine hyperbolic pi over c, as all of you know, is e power x minus e power minus x divided by 2. And therefore, practically sine hyperbolic x is e power x divided by 2. But on the other hand, whether you put e power pi over c or sine hyperbolic pi over c makes a lot of difference, essentially because the sine hyperbolic pi over c, Rademacher proved that this converges in fact, whereas the original e power pi over c does not converge. And the reason is not very difficult to see. because they differ by essentially an e power minus x. And once they differ by an e power minus x, and when x is rather large, then this e power minus x will not play any role at all. But on the other hand, if x is rather small, then e power minus x is not negligible, and that would play a role. And that's exactly what happens, because when you now write sine hyperbolic pi over c, and your x is pi over c, and c is something like a square root of n, then remember you are multiplying by lambda n, which is essentially square root of n, and therefore that would cancel. And then this pi over c times the lambda n is a small number, and therefore it doesn't really matter. But on the other hand, when c becomes bigger than square root of n, that number becomes rather very small, and therefore that e power minus x plays a role. And regarding this, I would probably make another comment. This Pn, okay, I will come to this a little later. Yeah, therefore, now write Snm equal to 1 over pi times square root of 8 to summation 1 less or equal to c less or equal to m, c power half ac of n d by dn of e power pi over c square root of 2 by 3 lambda n by lambda n, which is essentially the same result of Hardy and Ramanujan, except for the fact that now this e power pi over c, now you replace by sine hyperbolic. And what exactly happens? Sine hyperbolic x is x plus 1 over 3 factorial times x cubed plus so on and so forth. Whereas when you look at e power x, it will be 1 plus x square by 2 factorial and so on and so forth. There will be an x square term when you write e power x. But when you write e power x minus e power minus x, the x square term cancels and you have only x cubed. And that sine hyperbolic k lambda n by c, you divide by lambda n and substitute. Then you have a term which is k over c, and then 1 over 3 factorial k over c whole cubed lambda n square, and so on. And if you don't have the sine hyperbolic, but if you have exponential, then there will be also a term which is k over c whole square. Therefore, when you differentiate it now, the d by n you take, the first term is independent of n. Since the first term is independent of n, that won't contribute to the differentiation. And then what you get is 1 over 3 factorial k over c whole cube. Therefore, remember that you have a c cubed now. Whereas with the exponential, you would have got a c square. And now look at the summation. Summation c power of mod acn d by dn of sine hyperbolic k lambda n by c by lambda n. When you do that, remember we have already proved that this acn is of the order at most c, and therefore that will give you 1c, and then there's a c power half, and there's a 1 over c cubed coming from this derivation. Since there is a 1 over c cubed coming from the derivation, and with the c and the c power half, you get a 1 over c power 3 by 2. And once you have 1 over c power 3 by 2, it neatly converges. Whereas if you had the c square earlier, and then the c square term will give you 1 over c power half, and 1 over c power half over summation over c will not be convergent. Therefore, this is a Ramanujan series for Pn, which is absolutely convergent. And now let's see how does one prove such a result. Therefore, you have this partition. Partition function has been defined essentially combinatorically. Combinatorically, it has been defined that the number of ways a given integer n can be written as a sum of integers. But then this combinatorial way is not very easy to handle to get a formula like that. And what one normally does is a so-called generating functions. Now, what is a generating function? You look at the power series with the coefficients Pn. Therefore, you look at f of q, which is p of 0 plus p of 1 times q plus p of 2 times q square plus etc. p of n q power n plus etc. Therefore, this is the power series corresponding to the partition function. And once you have a power series corresponding to the partition function, there is something called the Cauchy integral formula, which would give the coefficients in terms of an integral involving f of q. And of course, this Cauchy integral formula, where you can only integrate only over the region where the FQ converges. Therefore, first of all, one should know where the FQ converges, and it's not difficult to see FQ converges when modulus of Q is less than 1, strictly less than 1. And since FQ converges when modulus of Q is strictly less than 1, that defines an analytic function. And then you can write the Cauchy integral formula that gives you Pn equal to 1 over 2 pi I into integral over any contour which is completely within the open unit disk times f of q into q power n plus 1 dq. And normally what you will take it is a circle. Therefore, you take a circle and then you integrate it. And in fact, the word circle method actually comes from that, essentially, because now one has to integrate a certain function over a circle, and how do we plan to do that? In order to do that, we have to understand what is this FQ. FQ has been now defined as a power series involving the partition functions. But then that alone is not sufficient. I mean, we need to know little more about FQ. And now, fortunately, there's a formula due to Euler which helps us. And the formula of Euler is P of 0 plus P of 1 times Q plus P of 2 times Q square, etc. P of n times Q power n, which is our FQ, is equal to 1 over 1 minus Q into 1 minus Q square into 1 minus Q cubed, etc. 1 minus Q power n. And this is really not difficult to prove. In fact, if you now take 1 over 1 minus Q, which is 1 plus Q square plus Q cubed, 1 over 1 minus Q square, which is 1 plus Q square plus Q power 4 plus Q power 6, etc. and then multiply, and then clearly you would see that the coefficient of Q power n is precisely the number of ways of writing n as sum of integers, and that will give you P. And therefore, the Pn is equal to 1 over 2 pi I integral over C f of Q, Q power n plus 1 dq. And the integrand is large in the neighborhood of points of the form Q is equal to e power 2 pi I A over C, where A over C is a rational number. And this is a very important point, because now when I want to talk about this impact of these ideas for other problems in number theory, and this observation that this integrand is large in the neighborhood of points of this form e power 2 pi I A over C, where A over C is a rational number, would play a major role. And first of all, this is somewhat easy to guess, and then the integrand is sort of a modular form. Using all those things, you can actually prove that this is in fact what happens. The contribution of the integral around e power 2 pi I A over C should correspond inversely with the size of C. Therefore, this is the situation where we are in. We are writing Pn equal to 1 over 2 pi I integral f of q by q power n plus 1 dq, and then you are integrating over a small circle, which is the red circle, and the unit, there is a unit circle which is the blue circle, and this unit circle has points like e power 2 pi I A over C, and this is the function. The problem from this denominator q power n plus 1 would come when q is rather close to 0, but we are not going to do that. We are actually going to take the circle rather close to the unit circle, which means that the radius of the circle is rather less than 1 but very close to 1. And when it's less than 1 but close to 1, then the FQ gives you a problem. For example, 1 over Q will blow up around Q equal to 1, and 1 over Q square will blow up when Q is equal to plus or minus 1. 1 over Q cubed will blow up again when Q is close to the third root of unity. Therefore, and 1 over Q power n will blow up when Q is an nth root of unity. Therefore, in a certain sense, you would expect that the major contribution to this integral would come only when Q is close to n e power 2 pi I over C, where C is somewhat small. For example, let us take C is equal to 3, then 1 over Q cubed will blow up there. 1 over Q power 6 also will blow up. 1 over Q power 9 also will blow up. And therefore, there are a lot of factors which will blow up. But when q is equal to -1, etc., then 1 over q square, 1 over q power 4, 1 over q power 6, etc. will go up, which essentially means that for smaller values of c, the denominator becomes rather very small, and therefore the whole fq becomes very big. But on the other hand, if the c is rather, when the nth root of unity e power 2 pi I a over c, when c is rather big, then the contribution may not come much. And in fact, that's exactly what Hardy and Ramanujan did. And in order before that, I should also point out that this idea was probably known to Ramanujan even before he left India. And in fact, here you are looking at a function Pn, and Pn is sort of an inverse of the so-called Dirichlet's eta function, and that is a modular form of weight half. And I don't think I am going to explain what this modular form business is, but even though that is very important for these calculations. And what Ramanujan was interested was another function called the theta function, which is also a modular form of weight half. And he was interested in the inverse, and he was even able to write the formula for the nth coefficient of the inverse of the theta function. And in fact, the first letter to Hardy, he writes, this is the equation 1.14, as Hardy writes. And probably, of course, I should urge all of you to look at the book by Hardy, which is the title Ramanujan, 12 Lectures on Subjects Suggested by His Life and Work. And there is also some sort of a sequel to this book, Mathematical Legacy of Ramanujan, by Ram Murthy and Kumar Murthy, and which gives you, in some sense, the developments later in the last few years. But in this equation 1.14, which you can see in the Hardy's book, Ramanujan writes that when you write the inverse of theta function and then look at the coefficient of q power n, this coefficient of q power n is 1 over 4n times cosine hyperbolic pi times square root of n minus sine hyperbolic pi times square root of n by pi times square root of n. And this is a formula which really impressed Hardy, but Ramanujan went a little overboard in his enthusiasm, and in fact he wrote that the nth coefficient is an integer rather close to 1, at which he corrects almost immediately in his second letter. He says, it is not the nearest integer as I have hastily written you before, but it's close to that. In other words, he immediately realized that it is not really a nearest integer, but an arithmetic formula which he writes. And that's exactly whatever that idea which he had for the theta function is the idea which works for the partition function also. Now we go back to seeing how to this Pn equal to integral fq by q power n plus 1. We want to see how we are going to do this integration. And the fq we have an idea, and fq is 1 by 1 over q into 1 by 1 minus q into 1 minus q square, 1 minus q cubed, etc. And now instead of doing it over a circle, we want to do it in the plane, and therefore we make the substitution q is equal to e power 2 pi z, where z is the real part of z plus I times imaginary part of z, and therefore e power 2 pi z is 2 pi I times the real part of z minus 2 pi times the imaginary part of z. And now we have also said that we need mod q less than 1, because that is the region in which it converges. Therefore, you cannot do an integration where a region is not convergent. And the condition that mod q is less than 1 translates to modulus of e power 2 pi z is less than 1, and modulus of e power 2 pi z, as you can see from the previous formula, is e power minus 2 pi a into imaginary part of z, which means that imaginary part of z has to be positive. And that is the substitution. Therefore, that's the region in which we are going to do this integration. And this imaginary part of z positive, which is normally called the upper half plane, that's again an important thing, and that is where all your modular forms do lie, and all the modular properties comes there. And therefore, now we make a substitution, and we call it p of z, which is f of q, where q is replaced by e power 2 pi z, and this gives you P of 0 plus P of 1 t power 2 pi z plus etc. plus P of n t power 2 pi n z, and you have the original integral f of q by q power n plus 1 dq, and we make this substitution. When you put q is equal to e power 2 pi z and substitute, then it becomes the integral I to I plus 1 pz into e power minus 2 pi n z tz. And of course, you will be wondering where this I comes from. And in fact, if you take the circle of radius e power minus 2 pi, if you take a circle of radius e power minus 2 pi, and if z goes from I to I plus 1, where I is the square root of minus 1, if z is equal to I is equal to, if you take I is equal to square root of minus 1, and if z goes from I to I plus 1, then you can say this e power 2 pi z goes round the circle of radius e power minus 2 pi once. And therefore, this substitution gives you the Pn to be I to I plus 1 phi of z dz, where phi is equal to P of z into e power minus 2 pi I n z. Therefore, this is in some sense more like a Fourier transform. And this phi z is analytic in the upper half plane, and this phi is also periodic modulo 1, because Pz is e power minus 2 pi n I z is periodic modulo 1, and Pz is also periodic modulo 1, because P of z is equal to f of e power 2 pi I z, and 2 pi I z is also periodic of modulo 1. Therefore, Pz equal to Pz plus 1. Therefore, this is the integral which we have to do. And now look at this. I like this idea of Hardy and Ramanujan, where they were only looking at the points e power 2 pi I a over c, where c is rather small, and then got an error term and things like that. Rademacher was able to look at all the points and do this integration. And therefore, let's just look at what is Rademacher's idea. Rademacher's idea starts with the so-called Faris series. This Faris series is a set of all rational numbers between 0 and 1 in reduced form, with the denominator not exceeding n. They are arranged in the increasing order. That is a Faris series of order n. For example, if you take 4, n equal to 4, and then you are looking at all the rational numbers whose denominator is less than or equal to 4, and then arrange them in the increasing order. And when you arrange them in the increasing order, you will get 0 by 1, 1 by 4, then 1 by 3, then 1 by 2, then 2 by 3, and then 3 by 4, and then 1 by 1. This is the Faris sequence of order 4, and this is, you can do it some more, and there's again a good theory of how to pass from 4 to 5 and so on and so forth, which I am not going to talk about. And now, taking any point A over C, you take a fourth circle. What is a fourth circle? This is the circle which is tangent to the real line, passing through the point A by C. Therefore, it is the circle and the real line are tangent to each other, and this is at A over C. The intersection of the circle and the real line is at A over C, and the radius is 1 over 2c square. And you can see that when c is small, then the radius is rather big, and for large c, the radius is small. And now you can, again, we are looking at the case n equal to 4 only. For n equal to 4, I can now draw the fourth circle. Therefore, the points which we have already seen are the points which are 0, 1 over 4, 1 over 3, 1 over 2, 3 over 2, 3 over 4, 1. And at 0, 0 is written as 0 over 1, and the radius is 1 over 2c square, as you can see. Therefore, it is that you have to take the denominator, square it, multiply by 2, and then take the inverse. Therefore, at 0, the radius will be 1 over 2, and at 1, and 3 over 4, for example, will be a very small radius, because it will be actually 1 over 32. And then you can actually, when you do this, and you can actually prove that given into 4 circles, either they meet either tangentially or they don't meet at all. Therefore, 4 circles are distinct rational numbers meet if and only if these rational numbers are a consecutive terms of a Faris series. When this is the case, the associated circles meet tangentially. And now we go back to. Therefore, what we have, when we go back to the earlier one, then integral from I to I plus 1 p of z e power minus 2 pi a dz. And this, as we have already seen, corresponds to a circle of radius e power minus 2 pi. But we don't want to integrate over the circle of radius minus 2 pi because the points e power 2 pi I into a over c, etc., which would make an impact on this function f of q, they will play no role at all in such a small circle. Now, you have to take really a circle which is radius is less than 1 but very close to 1, which is when you do this translation, q is equal to e power 2 pi z, that essentially translates to that you should do the integration more closer to the real line. And that's exactly what we plan to do. Therefore, from I to I plus 1, we really plan to move it closer to the real line and do this integration. And by Cauchy's theorem, that is allowed. How do we do that? And we take, first of all, n equal to 1, for example. Then there will be 2 4 circles, okay? And the 2 4 circles are shown. And then as the arrow comes, therefore you go I and take the first left 4 circle and go along that and see where it meets the right 4 circle and then go back to that. And that is the contour which we are going to do. And of course, this is not the contour. This is for I n equal to 1, and we are going to do it for n equal to 2, 3, 4, etc. Yeah, this is the contour for n equal to 2. Therefore, you take the 4 circle corresponding to half also, and then you go all the way up to this circle where it meets the 4 circle half, and then you go along the half and then go back to I plus 1. And then when you do that, then you get to 1 over 3. Therefore, again, you go all the way up to the 1 over 3 4 circle. And then 1 over 3 4 circle to 1 over 2 4 circle you go. And 1 over 2 to 2 over 3 you go. And then 2 over 3 to 1 by 1 over 1 circle you go. Therefore, you will take for each consecutive one, you just keep going along each of the consecutive circles. Therefore, this way you get a region. And this is a region in which we are going to integrate it. And you can do it for general n. When you do it for general n, then you are going for I to I plus 1, then you go all the way up to this I plus 1 business. And therefore, for any rational number x in 0, 1, the part of the 4 circle at x that belongs to the contour, that is denoted by cxn. Therefore, when x is equal to a by c, then when you do these things, and when you have this contour, therefore, it will come from the previous 4 circle to this circle and then go to the next 4 circle, and that contour is which is called cxn, and then you allow n tend to infinity, which means that there is no error term or anything like that. You are like taking essentially all the integration all the way out to I plus 1. And when you do that, therefore you have the integration over the 4 circles and summation over x belongs to q. And now how do you do the integration over the 4 circle? You can interchange it, and therefore finally you get, if you can use the dominator convergence theorem, for example, then probably you will get something like an integral I to I plus 1 vz dz is a summation over x belongs to q, which means that I am taking all rational numbers between 0 and 1, and then you have integration over the 4 circle of vz dz. And now the question is, how do we do this? Okay, now that is where this modulus idea comes, because then the phi z can be essentially written, because there is a transformation formula, and you can use the transformation formula and you can explicitly write the phi z and do the integration and so on and so forth. And that is not the point which I am now going to talk about. What I want to say essentially is that this particular idea, that you have a Fourier coefficients and then you are integrating, or even for example power series, and then you have a power series coefficient, and the power series coefficient is now written as a Cauchy's thing, and therefore you have an integral, and you are going to do it over the integral over the unit circle. Okay, you cannot normally do it over the unit circle, because on the unit circle the power series normally will not be convergent, which is the case, for example, for us. Here the 1 over q, 1 over 1 minus q to 1 minus q square to 1 minus q power n is not convergent on the unit circle, but just within the unit circle it is convergent, and therefore you take a circle there and then try to integrate. And most of the time, of course, you will not have a modular property, therefore you have to do something else, etc. And that has been one of the very important areas of research in number theory, where there have been many problems which have been worked out using this idea. And in particular, I want to talk about mainly about the variance problem. But before talking about the variance problem, I should also say that this is not only the variance problem, there are other applications also. For example, Goldbox conjecture. Goldbox conjecture is a statement which says that every even integer can be written as sum of two prime numbers, and which we do not know. But then you can ask a slightly weaker question: is it true that every odd integer is a sum of three prime numbers? And that has been recently proved, at least 5-6 years back, by Helfgott, who proved that every odd number integer is a sum of three prime numbers. And the idea of the proof is essentially by circle method. I mean, so this is exactly what we do. Okay, I will explain the variance problem, and therefore the idea for the Goldbach also would follow along the similar lines. And now there are other problems in additive combinatorics. For example, suppose you are given a, suppose you take all the integers, and all the integers would have all natural numbers. All natural numbers will have some nice properties. Okay, and now I can ask, suppose I don't take all natural numbers, but a big set of natural numbers, or what one calls the positive density of natural numbers, which means that essentially the number of natural numbers up to capital N which I take is at least constant times n. Therefore, the number of integers which I am taking, for example, is, let's say, bigger than 1/100 times n, then it is something called a positive density. Therefore, if I take a set of positive density of natural numbers, and one would like to know whether any of those nice properties which is true for all natural numbers, will it still hold for these numbers of the positive density? One easy question which you can ask is that if you take all natural numbers, then you can find out three elements which are arithmetic progression. Okay, take three consecutive integers, they already become an arithmetic progression. Therefore, this is another, in the other case, though we want to know that of course I don't have all natural numbers, but I have a sufficiently many natural numbers which I am taking. In fact, the number of natural numbers up to capital N which I am taking is at least 1/100 times n, and in that case, is it really true that this sequence will have at least three elements in the arithmetic progression? More generally, whether it will have k elements in the arithmetic progression for any given k, and so on and so forth. And the first result in this direction was proved by K. F. Roth, who proved, again using circle method, that it's in fact true that any sequence of a positive density has three terms in arithmetic progression. And now that is a very important result in additive combinatorics, and it has more generalizations, which I will not probably talk about. Let me talk about just the variance problem alone. And now what is variance problem? Variance problem is, in the original partition function, you are taking an integer and trying to write it as sum of positive integers. Here, you are taking an integer and then you are trying to write it as sum of kth powers of positive integers. And not only that, you want the number of summands to be minimal. In a particular, you want to know whether there is an S such that every integer n can be written as sum of s kth powers. And if such an n exists for every integer n, then that infimum is called little gk. And if every large integers can be written as sum of s non-negative kth powers, because for somehow what happens is the small numbers do have some idiosyncrasies and they sort of kill the things. And the more natural question is to look at what is capital Gk, whether every sufficiently large n can be written as sum of s kth powers. And the first result is Lagrange, where he proved G2 equal to capital G2 equal to 4. And variance conjecture is G3 equal to 9, G4 equal to 19, and so on and so forth. And Hilbert proved that GK is finite. GK is finite essentially by he used this idea that x1 square plus x2 square plus xn square power k can be written as summation ai ci1 x1 plus a etc. cin xn power 2k, by essentially saying that if you take a set of points and then take the convex hull of that and then take the GCD, and that can be written as a linear combination of the vertices of this convex hull. Anyway, then the natural question is, as I was telling you, that the small numbers are the ones which give you problem, and that makes a little GK rather very high, whereas capital GK you don't expect to be that high. Therefore, little GK is somewhat easy to guess what the value should be, just looking only at the small integers n. If a certain number is sufficient for all the small values of n, then hopefully that number is sufficient for all the values of n. And this idea makes us one guess that GK is equal to 2 power k plus the integral part of 3 by 2 power k minus 2. And such a result will not follow from the Hilbert's idea. Hilbert's idea actually gives you a bound for GK which is astronomically big. And now let's do this. Again, whatever we did for the partition function is precisely what we are going to do. More precisely, suppose you have a function f of z which is summation cn z power n, which is holomorphic. Then of course you can write the coefficient cn as 1 over 2 pi a integral or f of z by z power n plus 1 dz, where the integration is done over a circle of radius r. And in these problems, we do expect that the dominant contribution to this integral giving Cn comes from r sufficiently close to 1 from the neighborhood of point z, which is r e power 2 pi I p over q, where p over q has a small denominator q. This is the original idea of Ramanujan, that you can do all such integrations. You know, the whole idea is to do this integration. How do you do this integration? And the original idea of Ramanujan was that in this particular integration, the numbers with a small denominator, they are going to contribute. And if you can somehow do the compute what is the contribution coming from these numbers, and the rest of the contribution is something which you can ignore. And you apply this with f of z equal to gz power s, where gz is equal to 1 plus summation 2 z by n power k. Hardy and Littlewood got gk is equal to k minus 2 into 2 power k minus 1 plus 5. And the number of representations of n as a sum of s kth powers is given by 0 to 1 ft power s e power minus 2 pi a nt dt, where ft is summation e power 2 pi a x power k times t with 1 less than or equal to x less than or equal to p, with p is equal to n power 1 over k. Okay, there are a few comments which are important here. See, this essentially what I have done is, by ft, original ft was summation over x all the way to e power 2 pi a x power k times t. I mean, the x was going from all the way from 1 to infinity. Once you are having it essentially from 1 to infinity, then the point is that this series is not convergent on the unit circle. And since it's not convergent on the unit circle, therefore you cannot do it on the convergent in the unit circle. Therefore, you have to integrate over a circle of radius r, where r you go make it into 1, and that is essentially originally the idea of Hardy and Littlewood. But then it was observed that you really do not need to take all the x from 1 to infinity. You can actually truncate at p. And once you truncate at p, then it is convergent on the unit circle. Once it is convergent on the unit circle, then the original substitution q is equal to e power 2 pi z really makes the power series into Fourier series, and therefore you have this Fourier series formula, which is 0 to 1 ft power s e power minus 2 pi a t. And this is something which you cannot do in the partition function, because in the partition function you are using the fact that the integrand is a modular form, and if you do all this truncation, then the integrand will not be a modular form. You will not be able to do anything. But on the other hand, for these problems, anyway, this is not in modular form, even if you take up to infinity, and therefore you can as well truncate it so that you can really do the integration over the unit circle. From this starting point, Vinogradov used a Hardy-Ramanujan method together with a number of new ideas to get this bound gk is less than 6 times k log k plus some constant times k. And this is an effective method. And Vinogradov's method rendered the following two-step strategy. Compute an n1 such that the number of kth powers does not exceed s, and then direct verify. For small integers, you verify directly. Because all these ideas of essentially looking at the contributions only from a small denominator, that will give a what is called the major error contribution, and then there will be always an error which is the minor error contribution, and this main term will dominate the error term only when n is sufficiently large. And the years 1935 to 40 saw an immense amount of work, and a leading role in this effect was played by Pillai, which I will talk about. And Pillai, I mean, his contribution to Waring's problem, which is based upon this idea of Ramanujan, and which was developed by Hardy and Littlewood and then Vinogradov, Davenport and others, is he had an earlier education in Nagarkoil, and he joined the University of Madras, and he moved to Annamalai University, and he remained at Annamalai University 1929 to 41, and he obtained a DSc in mathematics from the University of Madras. And he proved that his important contribution is that he proved G7 is 143 and G6 is 73. And for K bigger than 8, it was already known essentially. The 6 and 7 were difficult cases, and Pillai was able to do that. And then the 5 was done by Chanjigran. G5 is equal to 37, and Sweat Dress proved G4 is 21. And the idea is, okay, there's the minor error contribution has to be estimated, and that involves a certain Weyl sum, and the Weyl sums, which means essentially you have to sum e of alpha n power 4. This means e power 2 pi I alpha n power 4 n up to p, and it is known that this number, this estimation is already known, and in fact for general alpha n power k, it was already known due to Hermann Weyl that it is p power 1 minus 1 over 2 power k minus 1 plus epsilon, but the O constant is very large, and then we found a method where we got an estimate which is slightly weaker in the exponent, but on the other, the O constant, it was much better. And that, and together with other ideas, finally gave this problem for G4 also. And now we started with the Srinivas Ramanujan. Let us end the lecture, since we are talking about the Waring's problem, with another Ramanujan now. And that is Chakravarti Padmanabhan Ramanujan, CPR. He was an expert in number theory and algebraic geometry, and he was also looking at the Waring's problem. And but he was looking at a more general thing. In his first year, he wrote up the notes for the algebraic function of one variable, and for his thesis written under supervision of Ramanathan, he proved that every cubic form in 59 variables has a non-trivial zero. The interest in the result is that the bound is independent of the number field. He realized that this method is equally applicable to Waring's problem, which means that he was looking at the problems, Waring's problem, over a number field, and then trying to see whether you can get a bound which is somewhat independent of the number field. Well, it can be a number field, and SKD with a set of dth powers of totally positive integers in K. And Siegel proved that there exists a G such that for any n in SKD can be written as sum of at most G dth powers. And Siegel conjectured that this G can be taken to depend only upon D, and it is independent of the field K, which is what C.P. Ramanujan did. And with that, I would stop. Thank you very much.
Thank you, sir. It was a very wonderful lecture. Gaurav, if questions are something there in the YouTube, can you post it, please? Gaurav and Bharat Bhushan. So, Dr. Ramanujam.
I think on the comments there are
Yes, sir.
some that you may want to look at.
Yeah.
So you can read the comments.
Have you flashing it on the screen?
Yeah. You just read. I will flash it.
No. Then it means that I have to go to the Facebook page, right?
No.
Oh,
Here on the left.
coming up. Sorry. Yeah. I got it. Okay. Sir, there is one question that has come here, which is, what is the use of geometric progression in real life? I mean, is there any real life example? That's one question somebody has asked.
I am sort of totally unprepared to. I mean, I think there are many books which you talk about geometric progression, what happens in the real life, etc., but something which I cannot immediately think of.
Yeah, so there are lots of comments on the lecture. I'll just, there is one question. I mean, if you can comment something about Ramanujam and the black hole. I mean, somewhere the Ramanujam's work are useful in understanding black holes, theories of black holes.
But again, without slides, etc., it's more difficult to explain. But what happens is, when Ramanujan came back to India, even then he was working, and then he worked on something called the Mach theta functions. And this Mach theta, and he wrote to Hardy that, I have found it very interesting examples of Mach theta functions. And this Mach theta function seems to be useful in understanding black holes. I mean, the string theories and black holes, etc. There's a lot of work on which comes from the Mach theta functions, which he did more or less on his after coming back to India when he was very seriously ill.
Yeah, thanks, sir. There is one more question. What is the geometrical meaning of second order derivatives?
Acceleration.
What is the geometrical meaning of second order derivatives, or the geometrical equivalent of second order derivatives?
Okay. Second order derivative is probably when the first order derivative vanishes, then you want to know whether it is increasing or decreasing at that stage, the neighborhood. But it's more the motion, that the acceleration, that is where the second order derivative is more useful, only in the equations of motions.
Okay. There is one request from one person who had participated, is a very young person. I mean, he is in 10th standard. So the question is also of that kind. I mean, he says that, can you say something, a very simple theorem or a special Ramanujam, special number connected with Ramanujam, and explain to him? Bharatwaj, Madhvesh Bharatwaj is in 10th standard.
Which is 1729 is probably what he has in mind. Okay, which is this number, which is the smallest number, which can be written as sum of two cubes in two different ways. That is 12 cube plus 1 cube, as well as 10 cube plus 9 cube. Okay, and that what is surprising is essentially that again he was ill, and Hardy goes to see him, and Hardy says that this is my taxi cab number, which it doesn't look a nice number. To which Ramanujan immediately said, no, Hardy, it's an interesting number. It is the smallest number which can be written as sum of two cubes. But on the other hand, I have also read somewhere, I have to double check that it is not something which immediately he was able to say, because it seems that in his notebooks, he has already made a lot of calculations regarding these things.
Sir, can I just add on this point? I mean, what you are pointing out, like, see, one of his article, which he has written in the Indian Mathematical Society's journal, In a way, he had referred to this expansion for this number. I mean, this.
Yeah, exactly.
Yeah, yeah, and also he was also trying to work out the near misses for Fermat's theory.
Yeah.
So
Yes.
basically, was something which is 1 plus or 1 minus, that kind of a stuff, and then there also he has mentioned this. I mean, that's
as Harley points out, each number was his friend. I mean, he was able to find out something interesting about each of these numbers. For example, Harley and Ramanujan proved that normally the number of prime factors of a number n is around log n and not the maximum that it could attain. The maximum that it could attain will be something like a log n by log n, but they proved that normally on an average the number of prime factors of a given n is only something like a log n, and these things a person cannot even imagine unless whenever he sees a number he tries to factorize how many factors are there, is there anything special about it, etc. There's a lot of calculations which he has done. In fact, it looks like that even for the tau function, I mean, this is, I think, what Professor Austerley told me, that even for tau function, whatever he has done, all those things, there has been a lot of trial and miss. There's a lot of calculations that have been done by Ramanujan before making even those conjectures.
Thanks, sir. I think we have come to the end of the lecture part. We have taken much of the questions which are here. I would just like to ask Dr. Ramanujan if you'd like to add anything. Otherwise, we can go for the conclusion. Dr. Ramanujan, do you like to add anything before?
No, I don't.
That's
Thank you.
So thank you. So I would request our director to formally thank our speaker and also conclude today's program. It was a very wonderful lecture, sir. Thank you for accepting our invitation to be part of this Ramanujan Yatra.
So I know Dr. Venkateshwaran has done the bit, and I think it's important for me to reiterate our heartful thanks to you, sir, for having accepted our invitation. And it was indeed very enlightening for all of us. And in our mythology, we have a small couplet in Hindi which says "Guru Govind dono khade kako logam pai." So when Guru and Govinda, both of them are standing, whom should we touch the feet? So I think it's important to touch the feet of Guru. And in this case, to get Govinda like you, our Guru, Dr. Ramanujam, did his bit. So I think we are equally thankful to Dr. Ramanujam for having this organized and having gotten you to this wonderful thing. So from the core of my heart, on behalf of Vigyan Prasar, Arivel Palagai, Dr. Venkateshwaran, Sri Kumar, Balakrishnan ji, Bhaskar ji, the entire team here in Vigyan Prasar, I take this liberty to, really want to thank you from the core of my heart, as I said, and also would love to have you in our forthcoming discussions as well, sir. There's a lot.
Definitely.
There's a lot. Yeah. So there's a lot that we could do together to make maths much more interesting and get the attention of all those people who claim to say that math is not interesting. So with this endeavor, I would once again thank Professor Balasubramaniam, Dr. Ramanujam, Dr. Venkateshwar and his team for having organized this wonderful lecture. Sir, please stay safe, stay happy, and have a great evening. Look forward to be working closely with you, sir. Thank you once again, Professor Balasubramaniam, sir. No.
Thank you. With this, we would be ending our live broadcast now. Thanks to all the participants who have joined us through Facebook and YouTube for this live program, and also people who might be watching this later subsequently in Facebook or YouTube. Thank you. Thank you all of you.
Thanks.